Clymer, Dr. Clymer. I taught systems engineering for 35 years at California State University at Fullerton. And of course, we're right in the middle of aerospace, so we had all kinds of students from, Rockwell and Hughes Aircraft, and all those guys were around there. But I started at General Electric in systems engineering, and that's where I got the idea for this simulation-based design. The idea that you're given a problem, given a mission statement, then you want to figure out what is the real problem and what is the best solution. And so this was like 57 years ago, and I continued working on this methodology until now. And so it's basically come to fruition with tackling this problem, which is almost impossible, as you will see. But at the end of the talk, I have an example of a problem I did for the Navy, where we worked out the design of a kill vehicle to knock out reentry vehicles. This was a perfect example of this methodology and how successful it can be. So, okay, let's go. So the title of the talk is Simulation-Based Design of the LENR System, Low Energy Nuclear Reactions. So what is low energy versus high energy? Okay, low energy, basically we use low energy light, because the only thing we can use is light, to interact with matter in the material universe. And the light sequence basically is a sequence of light at the correct time, and in order to create new matter, atoms, fix old matter, deal with other kinds of disturbances, like at Skinwalker Ranch, where they got this huge disturbance in the middle of it that's created a huge bubble of energy, and nobody understands it. Well, we do. Okay, so then there's high energy, and you all heard of these particle accelerators. A tremendous amount of energy is being expended in order to accelerate particles, bang the particles together and see what comes loose. And they're identifying all kinds of new particles doing that. But I've just been informed that one of the problems they're having is that when you do that, you create this huge bubble of energy, and they're afraid that they don't know what it's going to do. Well, we do. Okay, so I want to add some things to what your handout has to it. Okay, the main presentation topics. Okay, we have I call it the OPM CSS, Operational Evaluation Modeling for Context-Sensitive Systems, the Simulation-Based Design Methodology. And basically, in a nutshell, given the mission statement, what we do is we determine what is the real problem and what is the best conceptual design to solve the problem. We have a model of what we call the IU, Information Universe, Material Universe, IUMU system. And this model describes how the IU communicates with the MU in order to deal with disturbances, one of which is to create new matter or to repair matter. But there are other kinds of disturbances. Okay, so the communication is based on what I call a linguistic model described by rules. So we can learn rules that will, a sequence of rules that will have the benefit that we want. In other words, we want, in our case, we want to produce new physics. We want to disturb the process that's going on and create new physics. And we have this SUSY model that Dr. Johnson has created, and it's too complicated to talk about here, but it's in the paper. And at the end of the paper, there are several papers by Dr. Johnson and others that describe what this is. And if you're really interested, you could go read those, because there's a lot to this. It's like drinking out of a fire hose. But we won't get that today, because we're interested in the system design, simulation-based system design. Okay, the last thing, or one of the other things, is reinforcement learning. Okay, the classifier system block learns to a sequence of rules that satisfies a goal. And in order to learn these, we have to have some kind of measurement of how close that sequence of rule achieved the goal of the system. And so you basically you're learning a sequence to solve a problem or a plan. So those are kind of the most important points. Okay, the methodology, as I said, basically, given the mission statement, we want to determine what is the real problem, what is the best conceptual design to solve the problem. And okay, so the model is described, the operational model is described using a set of icons, which we'll be talking about. And then in order to, we could just draw a diagram with icons on it. Some people would be happy. But if you want to actually execute the model, simulate it and study it, then you have to have a simulation model, right? So we go the next step. We not just block diagram, we have a simulation model. And it's based on the same operational process and icons. Okay, so the key point here, take home, OpenCSS finds the correct actions at the correct times, consistent with all other concurrent processes to optimize system effectiveness. Every system that you'll ever run into looks like that. People you may not, know that. Most of you do, probably, because you're simulators. But anyway, that's the main point of the whole thing. Okay, now the interesting thing about LENR is that this has been going on for 90 years. The Germans were working on this. The Russians were working on it. We were working on it. I mean, people have been working on this forever. And I got two here. The first two examples are on our team. We have Amar Vakil. He was working on this on cold fusion in the early 90s. And then Fedor Rochin and Sergei Godin are working on it now. They've been working on it for years. And they've experienced some interesting things. And one of those is that when you try to interfere with the material universe, it creates a big bubble around your work. And they experience that themselves. We probably won't get into that, but that's into the model. Okay, so from all this and with Dr. Johnson's theory, we've been able to work out what is the format of subatomic control processes. In other words, these processes are based on light frequencies at a current time. You have a sequence of these. And for the right light and the right timing, then you'll create an atom or fix an atom or mitigate a disturbance. If it's not right, you have chaos, and then the thing can blow up, which has happened to people before. Anyway, so we will continue to do experiments with LENR. The Russians are doing them and other people, and we hope to verify what the format of the process. Okay, the key point. Each subatomic regulatory process is a sequence of the correct light frequencies at the correct time to avoid LENR system chaos and subsequent meltdown. So you don't do this kind of thing lightly, because if you don't get it right, there's a tremendous amount of energy in the information universe that you can turn loose on yourself. It's not like atomic, it's a whole lot more than you can get out of atomic. It's almost an infinite amount of energy can be released if you do it right. Okay, next, you got it? Okay, the information universe IUMU system. So we've worked out this model, and the mission of this system is to regulate the material universe, to fix disturbances, to lower entropy. In other words, we would like to do this in an orderly way. And the universe does. The universe has converged to minimum energy, minimum, basically it's converged to the perfect chaos. So lowered chaos. So things do happen, but anyway, the real system, the IUMU system, is converged. All the isotopes are stable. You don't have anything blowing up. The real problem in all this is that quarks and bosons, which are the building blocks of atoms, don't live long. They die or disintegrate, whatever you want to call it. So you have to have. There's got to be something to regulate that, to create new atoms, to repair atoms, to deal with disturbances. Okay, so the information universe communicates with the material universe to regulate the material universe. The communication messages are based on context-sensitive language, using message generating rules, and so that classifier system can learn those kind of rules. That's the main thing. Another thing that we've learned is that there's a lattice structure. The material universe is a lattice structure of IU agents that apply message rules to communicate with a Planck scale element at every XYZ point in the MU. And so you have the information universe where there are rules, there's intelligence. And then in the material universe, you have these agents, and they communicate in order to regulate the material universe. And so the key point, the IUMU system model provides subatomic process structure and operations needed to achieve LENR system designed to produce new physics. Again, it's systems engineering. It's simulation-based systems engineering all the way. Okay, now this is a model that I've got going. First, you'll notice this sequence of icons. That's an icon, that's an icon. These icons describe communicating parallel processes. Next thing is, you see there's only one sequence there? Well, it's actually duplicated 1,000 times. And this allows you to have a varying number of concurrent processes in your model. Right there is the classifier. Let me venture over here. So these are the icons. And here's the classifier block learns the rules. And then further on down, the sequence of rules is then rewarded or punished based on how closer you got to the goal. And then the next thing over, I compute the entropy. because anytime you have a system under regulation, entropy will be reduced. And the reason is because you're generating the rules, and it's eliminating most of the things that could possibly happen from happening unless it's productive, and it has to be something that contributes to the goal. Otherwise, so all these actions that are part of chaos just don't never happen. So the entropy drops, and you'll see right here. This is measured entropy, and it's dropping down as you learn the regulatory rules. Okay, key point. The process sequence shown is duplicated 1,000 times to create a 3D lattice structure of IU agents for the IUMU system simulation. And these agents communicate in the lattice. So you can just think about it. The way I think about it, we have a 3D lattice. At each point in there, there's a bubble. That little bubble is an engine that takes energy from the IU, processes it, and generates helium or hydrogen or some other element, or it fixes an atom, or it works on a disturbance. Okay, that's good. Okay, what does the classifier system do? Well, basically, it takes what I call the system state as input. In other words, where are we now? It applies a rule and creates an action, which then results in going to the next state. That's the fundamental what it does. So there's more details on there. We'll skip those. Classifier system operational details are discussed in the paper and available for experimentation in the 2009 Wiley textbook, Simulation-Based Simulation-Based Engineering to Complex System. It's still available on Amazon. And the book comes with a disc that has this system, and all the models on it. And you get the book, you get the software, you can run the software, you can experiment with this. There's a classifier there, there's a evolution algorithm block, there's the blocks that allow you to create a process. Anyway, you can do your own, you can roll your own if you want to. If you're really interested, you got that option. Okay, the key point, IUMU this simulation model used reinforcement learning to learn rules, which is a sequence of rules, to create an optimal sequence of subatomic process actions to produce new physics. So basically, the systems engineering is simulation-based systems engineering is trying to solve the LENR problem. But it's a general systems engineering methodology. Apply it to any system. Any system you have the mission statement for is going to look like this. Okay, the SUSE model. Okay, like I said, this is something that I'm not going to talk about. I was going to. You can read these. You got the handout. You can read these. The key point: the SUSE inversion model allows the subatomic regulatory process to be inferred from known physics in the LENR system experiments when nothing about the IU is directly observable. See, that's been the problem for ever since people started thinking about this, is that the information universe is beyond our material universe. They knew there was a Planck scale, and they've been talking, and they knew that there was something beyond the Planck scale. There is. There's another dimension of reality, which is where the information universe is. And the information universe has access to an infinite amount of energy, and the energy comes into the material universe as light, and then the light is the energy that's used to control. Anyway, so Basically, the model allows us to go beyond what we've been able to do up to now. We have a model of the IUMU system, and we have an idea of what the process looks like, subatomic sequence to create or modify it by matter or solve disturbances. Okay, so this is what we've come up with so far, the design. Okay, first of all, the system consists of a computer-controlled light message sequence generator, and subatomic process state sensor, which is probably just measuring the frequency of the light, because that's what the state really is. And but I may need something else in order to control reinforcement learning. So we're working on that. Excuse me. A computer sends regulatory messages to the material universe to disturb subatomic process. Non-stable isotopes are created, and these isotopes will have the properties of the new physics that we want. And people are doing that now. They're getting all kinds of new physics. They just don't know how to control it. And we're going to use reinforcement learning to learn the sequence of rules that will result in the control of the new and construction of the new physics. Okay, key point. LENR system's low energy light is used to control subatomic regulatory process to produce new physics. Again, it's the basic structure of a system, is that you have a sequence of actions at the right time. And they have to be consistent with all the concurrent processes that are running. That's it. That's the model. And any system you ever want to think about will have that structure, an operation. Okay. So, how am I doing on time? Huh? Okay, so I better say. Okay, so these are the conclusions. You got the handout so you can look at the conclusions. Basically, I told you what I'm going to say, and in that conclusion, I'll tell you what I said. Okay, so anybody have any questions? Yeah.
So when you say like produce new physics using the LENR model, can you just plug that into the SUSI model?
Sorry, I didn't understand. Do you hear that, Valerie?
This one? Yeah. So when the key point says like regulatory process to be inferred from known physics, and the next slide says like, okay, we are producing new physics based on the model. Can we use the new physics and plug it into the SUSI model and gain something?
So the new physics that are created from the LENR model, is that able to be put into the SUSI model? Is that what you're saying?
Yeah.
The SUSI model describes how the process. It's a model of how the IUMU process, how that sequence, what it looks like. And the other thing is, you're wondering what is new physics? Well, one thing is if you can pull energy in, then you can create electrons in the processor, and so you can pump out electric current all from the vacuum. So you can generate electric power. We already have one experiment where let's go back here. Yeah, go to here. Slide 4. Anyway, Victor Clymer was able to get an unlimited number of photons from the IU. I mean, he had a COP of like 1,000, he'd put in one photon and he'd get 1,000 out. And where did they come from? Well, obviously they came from the outside, the IU. And so what we're talking about here is a model process for controlling that kind of thing. We want to be able to get a continuous stream of proton or the light or electric, or we might want to control gravity. So the process going on in the bubble affects gravity. Gravity increases, decreases. It also affects compression of space and the expansion of space. So if you set it up to do one of those things a lot, then you would be able to have lower gravity or no gravity. That's one of the things the researchers, the Germans, were working on. So does that help? Let's put this one back up. I want to talk about this one. How much time do I have? Huh? 5 minutes? Okay. So this was a problem I worked on a number of years ago. We had a SIBR, a Navy SIBR, and the problem basically was we would like to have a kill vehicle hit a reentry vehicle and destroy it. That was the mission. And so then what are the real problems? Well, the kill vehicle has a sensor, an IR sensor, which forms a cone. And so as the kill vehicle approaches the target, the cone shrinks. And so the problem then is to keep the target in the field of view. That's the problem. That's the real problem. The second real problem is, how do you recognize the objects that are up there? In particular, how do you recognize, the target from the other stuff? And so the basic idea that I came up with was that all these different objects have a different kinematic motion, and the kinematic motion modulates the signal to the IR. The IR signal has features in it that come from the kinematic motion of the object. So I developed a program as an evolutionary neural network combined with an induction program. So it would take, I take the features, I don't know if you're familiar with information waves, but an information wave will have a sequence of different frequencies that define the signal. And so each one of those can be considered as a data point, a data value in the data space. So the program was able to take a very large data space and map it into feature space for the classifier block. And then we were able to learn the rules that would then be able to recognize what object was in the field of view, each of the objects in the field of view. So then the next thing we did, I created what is known as the center of gravity. I used the rule would give you a probability, and so you could create the center of gravity of all the objects. And so then you steer for the center of gravity. And as the kill vehicle comes in, of course, its target's always in the field of view. And when you get close enough, it's 100% probability that that's the target. And so we basically steer towards that and hit it. And then I developed a simulation. It was an Oppum CSS simulation, just like the ones we talked about, except it had one additional feature. It did continuous time simulation, because we were simulating the kill vehicle guidance. And so we would guide the kill vehicle to the target using a guidance algorithm based on the center of mass. And so anyway, it just steer right in there and whack it and So then we got data from real firings, and we ran the data through our system, and it killed the target 100% of the time. In other words, those rules were very general and robust. It was killing things it hadn't seen before. Okay, so there's a paper that you can get. It's on ResearchGate, object classification from nonlinear data spaces. And I recommend that. Something to read. Okay, who's next?